In this video, we will discuss acid strength in terms of acid dissociation constant, which is also known as acid ionization constant. We have seen these strong acids, right? And now let us see the formula for these strong acids and general classification based on the number of hydrogen atoms in them. So we have first, second, third, fourth, and fifth. We can see that there is one hydrogen. So we call that one as the first five we can call monoprotic. Mono means one, protic is hydrogen ion, so monoprotic acids. And the sixth one, we can see two hydrogen in there in sulfuric acid. So we can call that one as diprotic, which means it has two acidic hydrogen atom or protons. And now look at the first three acids. It contains two elements and last three acids contain three elements. Also, in the naming section, we learned if there are two elements present, we call it as binary acid. And if there are three elements present, we call it as ternary acid. And now, based on the elements present, we can classify the first three acids as halo acids because there is a halogen present in it. So, chlorine, bromine, and iodine, they are acids. So, we can call these halo acids. And the last three, we can see that oxygen present in it, even though there is a halogen here and different elements in there. But in general, all three contains oxygen. So we call that one as oxyacids. So in oxyacids, the acidic proton, that is hydrogen, is attached to the oxygen present in that acid. So these three acids, oxyacids, are strong oxyacids. And we have weak oxyacids as well. They are phosphoric acid, H3PO4, nitrous acid, HNO2, and hypochlorous acid, HOCl. Now let us see the acidic strength. So if we have an acid, the same halogen, and the number of oxygen atom is different, we can see that when the number of oxygen atom is more, that acid is going to be more acidic. Say for example, HClO4 got 4 oxygen atom, HClO3 3 oxygen atom, HClO2 2 oxygen, and HClO only 1 oxygen. So HClO4 is going to be more stronger and all contains the same halogen, Cl, chlorine. And now what's the reason for that one? We can see that the hydrogen attached to oxygen. So oxygen is more electronegative. So what it will do is the shared pair of electron will be moved towards oxygen because it is highly electronegative. And in this case, we have two oxygen. So it will pull the electron more strongly than one oxygen. So this hydrogen will remove as proton easily than with the one oxygen. Same explanation goes here. If you have three oxygen will pull that shared pair of electron towards it and the hydrogen can be released as proton easily. And if there are more oxygen, the same thing repeat. That means the pull will increase towards it, the electron density will increase towards it, and the proton can be released easily. So same explanation we can give if there is acid with a sulfur, the same element, but the number of oxygen atom is more in H2SO4 and in H2SO3 we have only 3 oxygen. So H2SO4 is going to be stronger than H2SO3. Now consider these three acids, HOCl, HOBr, HOI. So what's the difference from the previous acids? Here we can see the number of oxygen atom is same, but the electronegative element present is different. So chlorine has more electronegativity than bromine, and bromine will have more electronegativity than iodine because we know from top to bottom in a column in the periodic table, the electronegativity decreases. So chlorine to bromine to iodine, the electronegativity decreases. So chlorine has more electronegativity. So the shared pair of electron will move towards chlorine and the hydrogen ion can be removed easily in HOCl than in HOBr. And HOBr will remove that proton easily than in HOI. So the electronegativity difference is the reason for the acidic strength here. And now let us explain the trend for binary acid. That means if the acid contains only two elements. So in that case, we can explain for a group and period in different ways. For a period, we will explain in terms of electronegativity. We know that from left to right, the electronegativity increases. When the electronegativity increases, the acid strength also increases. So that means along a period, the acid strength increases from left to right. So when you compare the examples here, HF will be the stronger acid. And along a group, what happens? Along a group, when you move from top to bottom, we are going to explain in terms of the size, not in terms of electronegativity. So when the size increases, the acid strength increases. So from top to bottom, the acid strength increases. So when you look at this example, we can see that fluorine, chlorine, bromine, and iodine from top to bottom. So the HI will be the stronger acid and HF is going to be the weaker acid. That is along a group. The reason for that one we can explain in terms of the size and the polarizability. So when we consider the group, when you move from top to bottom, what happens? The size increases. So the fluorine, chlorine, bromine, and iodine. So iodine is going to be the largest and fluorine is going to be the smallest. What happens for this size increase is when the size increases, there will be charge separation. That is for temporary charge separation will be there. We call that one as polarizability. So when there is more charge separation, the iodide ion formed from the acid is going to be more stable compared to the fluoride ion formed from the acid. So this is going to be less stable. That is the reason. So the stability of the iodide ion makes it more acidic. So we can compare the acid strength like this. HF is weaker and then we can write HCl is more stronger than HF and HBr is more stronger than HCl and HI is the strongest among all these acids. So how exactly we can measure the acid strength, whether it is strong acid, whether it's a weak acid, but if we have two strong acid, which one is going to be stronger? And if we have two weaker acids, which one is two weak acids, which one is more weaker? So for that one, we use acid strength and by using an equilibrium constant, acid dissociation, how much it dissociates. Okay, how can we do that one is when an acid react with a base, what happens is this electronegative, that is the negative ion here, which is electronegative than hydrogen, what it will do is it is going to take that electron towards it, the shared pair of electron here. One line means two electrons, right? One from A and one from hydrogen. So what happens? That shared electron is moving towards A. It's a little far from A and this is going to have a slight negative charge. We call it as delta negative. That means it's a very small charge. And hydrogen will have a delta positive charge. So it develops charges. So this hydrogen now is proton because the hydrogen giving that electron or A is taking that electron from the shared pair. So that proton is actually taken by or it is moving towards this lone pair, correct? So we are always showing by drawing an arrow like this. From the tail represent where is it moving from the starting point and the head shows the target. So that's how we have to show. That is called curved arrow method. So we have to show the curved arrow to show that where is it moving from and towards which one. Where is the target and where is the source. So it is moving like that and you can see that this lone pair is moving or the electrons are taken from this lone pair and it is bonding with the hydrogen ion. That is going to be the slight positive charge, correct? So we will have A negative here and we will have the hydronium ion here. So that is H3O positive. So that's a hydronium ion we are getting. So this is important, how to draw the curved arrow from the source to the target. So that's what we have to learn, how to write the acid-base reaction. Okay, so the point is, how can we determine the acid strength? So we have the products here and we have the reactants here. So if it is strong, we will have only one arrow. But now you see that one here, you can see one arrow moving forward and the other arrow moving backward. So double arrow. That means it is not strong acid. It's not strong. So that means partial ionization happening here. All right. Okay, but still we have some products. So what we will do is we will see the ratio. So how much product is formed, okay? How much concentration of the product, and we will divide that one with how much reactant, what's the concentration of the reactant. We will take the ratio. We call that ratio, remember, we call that one as equilibrium constant. Which is expressed as KEQ. So this is nothing but, since it is for acid, Ka. A stands for acid, EQ in general. So if it is specifically for acid, we will call it as Ka, that is called acid dissociation constant or simply acidity constant. Okay, so product over reactant we are writing. So what are the products here? We have A minus and we have hydronium ion. And what are the reactants here? We have water and we will have the acid. So water concentration, we never use that one for equilibrium expression, right? So we don't consider the water concentration. It is just like a constant, or we don't take that one for liquids. So now here, this is the acid concentration. So the only acid concentration will be in our equilibrium expression for the acid. So acidity constant or acid dissociation constant Ka equal hydronium ion concentration times A minus concentration divided by acid concentration. That's how we will decide how much is dissociating. If it is more dissociating, we will have Ka value high. So that means going to be it's stronger. Okay. If Ka value is smaller, we will say that is weaker acid when you compare two weak acids. Or any two acids, we will see that Ka value. But we don't talk about the Ka value for strong acid because it is 100% ionization. So we will just have the products. We will never have the reactants left. So normally we talk about this one only for weak acid. Okay.